Good morning, everybody in smoky California. Good afternoon and good evening. And for those of you who haven't joined now, hello in the future. My name is Victoria Vesna. I direct the ArtSci Center. I'm also professor at Design Media Arts at UCLA. And we have been very fortunate to have opportunity to collaborate with the Fraunhofer Institute for Digital Medicine. Last year and the year before, we did some workshops together, and we're now happily having one of our alumni, Eli Joteva, as artist in residence. I'm very pleased and grateful to Dr. Mathias Neugebauer, who joined us today to talk about medical imaging, and also for artists who are interested in this area that's becoming really, really important now with all the health issues we're all facing. It's become such a critical subject to address. And I think for art science collaborations, it's really wonderful that you are taking the time to give us a talk about this. So, welcome. And welcome from Bremen, I guess.
Yeah, thanks a lot. Thank you for having me here at your program. And so I'm Matthias Neugebauer. The first contact I got to medical visualization was during my studies. I'm actually was studying computer visualistics. It's a quite interesting course where you deal with standard topics of computational science, but you also look into other areas. And one of those areas was also medicine. And I really got hooked when I first had this interception between biological data and computers, and what you could do with this interesting input and what outputs you could generate. And also I did my PhD on complex flow visualization in the topic of cerebral aneurysms. Yeah, and then I got the chance to work at Fraunhofer Mewis, which is very interesting. A lot of topics you can work on, different fields. Yeah, and still I'm dealing a little bit with visualization, more with data processing currently. But still I'm happy to give you a bit of an insight on the basics of medical visualization. So
Wonderful.
you could say this is more a basic introduction. A little lecture, you could say. So I will just start now by
Thank you
sharing.
so much. We really appreciate the time you took to show us this. Many artists are very interested now in medical visualization.
Yeah, cool. Yeah. So at Fraunhofer Mewis, our research is mainly focusing on software solutions, and those software solutions are based on the various types of medical data. One type is, of course, images, and with those software solutions, we support various clinical processes. An example would be treatment planning or also therapy decision support. And within those projects, we of course also create images from the medical image data. And those images could look like this. Here we have an example of an anatomical 3D image. We see here some anatomical structures. Specifically, we are looking at the heart right now, and we also see some rib bones. So this would be an example for anatomical image data. On the other side, image data could also look like this when we visualize it. This is functional image data. Here we are looking at blood flow also in the heart. And those two screenshots are taken from a short movie that we have put up on YouTube. It's called A Virtual Journey Through the Heart. And we will also have a look at this video at the end of my talk. There's something special about the basics of this video, because most of us know medical visualizations in some form or another from, let's say, TV or movies, and those visualizations might look like this. It's a very nice, detailed example of a model of the human heart. But this model was created by an artist. A lot of medical knowledge was put into this image, but still it was created artificially, while the images that we are looking here are, let's say, directly taken out of the patient by means of imaging systems. And I would like to present to you how those images can be created. And but first of all, I want to give a short introduction in the general field of visualization. So when I talk about visualization, I mean the very basic and broad process, to make some kind of structured information that surrounds you somehow visible. So it could be anything. It could be, of course, data points that you have gathered with some kind of device, but it could also be quite abstract things like processes, even ideas that are drawn on some kind of flipboard is some kind of visualization. So in a very basic sense, visualization means that you have some concept, some structured item, and you map it to some visual representation in order to make it easier understandable. And to be a bit more specific, I want to show an example from our everyday life. So at least if you are located in Germany, you would know a sign like this. It's a sign that you can find on German highways. And yeah, it gives you a very focused information of things that you might want to know, for instance, on which highway you are on and where you can leave this specific highway in order to get to another one or to a city. And we already see that this visualization focuses only on certain core aspects and omits a lot of different information that are at your current location on the highway, for instance. Another similar example would be a slower kind of transportation. It's a public transportation. What we see here is the public transportation plan layout of the city of Bremen. That's the city that I'm in right now. And we see quite nicely laid out all the different lines and routes. We also see transit points and central stations mapped to some rectangular structures. So, but again, we can assume that a lot of information was reformatted in order to create an image like this. And if you compare this to the original layout of the city and this location, we see that a lot of things were changed. For instance, the Weser is just represented by a line, even though it's quite organic in this area. We also see that those two bridges are more or less the same diameter, but in our graph, they are quite different. So something was done in order to reach a certain goal. And this is our visualization goal. So the basic idea behind this plan on the right side is to give you fast an overview of the routes. Other information are omitted in order to support this visualization goal. So only specific information were extracted from the original raw data, let's say the layout of the city of Bremen. So only stops, routes, and connections were mapped to visual representations that allow you to get an overview fast. And this is a quite nice example for a very basic principle in visualization overall, but also in medical visualization. It's a so-called visualization pipeline. So normally you start with some kind of raw data, and then you do some kind of processing, remapping of data, deriving new data, and then once you have done this, you decide for an appropriate visual representation of this filtered and processed data, and then create a visualization that is hopefully useful for your visualization goal. So, but not only the data and the processing is important when you create visualizations, but also the observer who will work with your visualization, who hopefully will gain some new knowledge and new insights from looking at the visualization. And even though your visualization might consist of items that are known to everybody, the whole context needs to keep in mind that the observer has some background knowledge that must be met. So for instance, Here we have an example again for a German street sign. If you have a German driver's license, you might be familiar with this street sign. It's a Spielstraße, so it's a street where children are allowed to play on. This is shown in this little scene. But of course, if you didn't take a German driver's license test, you might not be familiar with this kind of visualization, even though all the items are known to you. You know what a house is and that this is a car and some persons on the street. And there was one funny story years ago. Tom Hanks was visiting Germany and he saw this sign. It was full of interesting items, but he couldn't make any sense of the overall meaning of the sign. And his interpretation, if I remember correctly, was that the child lost the ball while they were driving along the street, and now they had to stop the car in order to get the ball back. So you have always to keep in mind who you are creating visualizations for to reach the goal of providing insights and additional information. And this is also true for medical data and medical visualizations. We all, or most of us, are familiar with this kind of device. It's a fitness tracker. So it's a little device that you carry around, and it gives you information about your medical status, for normally the heartbeat. And here we see how this is visualized. So we see a number down there that represents the beats per minute, and maybe we also see a little animated icon that shows that the tact of your heartbeat. And it's useful for everyday use when you go jogging or something. But for medical experts, this kind of visualization would be unsuited because they need more details about the dynamic behavior of your heart. And they would, for instance, choose a visualization like this. Here we see a one-dimensional medical data visualization. It's the data taken from a so-called EKG, where the currents in the heart are measured, and then you get a nice curve like this. And from the different slopes and peaks, a medical expert can derive detailed knowledge about the current status of your heartbeat, for instance. So this would be an example for an expert visualization of 1D medical data. Here I have an example for two-dimensional medical data. Here we see slices of a human skull. We can see a bit of the eyes and also the brain. But we also see that there's something overlaid over the slides, and this is functional data gathered from a specific imaging process. And here we see, for instance, the intake of oxygen at certain locations of the brain. And from this, we can derive the activity in these brain regions. This would be a static image. You could also look at dynamic medical data. Here's another example. Again, we are looking at the brain, but this time we are looking at the temporal changes when fluids diffuse in the brain. So it's diffusion imaging. And down there, we have a quite complex visualization of the different temporal curves of the diffusion in the brain. And from this, experts can derive whether or not a patient, for instance, had a stroke and how much the brain is affected by its current situation. So this is an example for dynamic data. Still, we are in a bigger scale. We are looking at the complete head, for instance, but we could also go quite small and look at specific cells in the human body. Here, a specific microscopic image was taken, where you can see specific proteins that are present in cells, and from this you can derive the cell type and, for instance, the status of a biopsy that you have taken from a tumor. We could also go quite big and look at complete populations, where we gather within a study samples from thousands of people in a population, take laboratory values from them and images, and, for instance, try to derive disease trends in larger populations. And this would be more like a statistical view on medical data. So what I wanted to show with this is that there is a broad range of data, and even this is only a very small section of the kind of data that we might be dealing with when we create medical visualizations. But to narrow our scope a bit down within this talk, we will just focus on the visualizations that were also mainly used in the YouTube video that I mentioned earlier. So we will focus on this kind of medical visualization, which we could name a three-dimensional image visualization of anatomical, but also of dynamic data. Yeah, to understand how those images are created, yeah, as I mentioned earlier, these images are based on real patient data. So in order to create a meaningful visualization, we first must understand how the data was gathered and what kind of basic information is encoded in the data that we will use to create an image like this. And this specific example was created based on a CT scan. So we will have a short look at what this means. CT stands for computed tomography, and tomography itself means that you have an imaging process where you only take a small slice out of a bigger object, or in this specific case, from a patient. And yeah, here we see the basic layout of this process. So the patient is inside of the scanner, and we have a radiation source on one side and a radiation detector on the other side. And the source will send a very thin and narrow low dose X-ray beam through the patient. And X-rays get absorbed by structures that have a high density. So if the beam passes through something in your body that has a high density, it gets absorbed and less radiation will reach the detection unit. And yeah, from this profile, we can derive information. For instance, you know this kind of projective CT images if you had maybe a doctor's visit where an X-ray was taken of you, or if you went to a dentist. So you see how these images look like. And in this case, we would get one projection image in a very thin area from one direction. But of course, we want to get a tomographic image. So in order to get this, the radiation source and also the detection unit are rotating around the patient. So we get signals from a lot of different directions. And those profiles, those signals that we gather can be recomputed into a slice image from this specific location. And then we would get a slice like this, but we don't only want to have one slice, but several along the human body. So the radiation source and also the detection unit is moved along the main body axis of the patient. And yeah, once this is done, we get images like this. You see down here this little animation which goes through the body along the main axis. Yeah, so our result of this process would be an image stack like this. Here we have again a specific region was chosen. Here it is the head. Here we see the upper skull area. Then we go into the middle center of the head, and we end more or less on height of the nasal cavities. When we focus now on one specific slide, we of course see that this picture has different intensities. Some things are white, other things are more gray, and there are also dark areas within the skull. So this intensity has actually a physical meaning behind it, because as we mentioned earlier, this image was created by X-rays and the absorption of X-rays within the body. So this must have something to do with the absorption. And the quite nice thing that of CT imaging is that there are a lot of standard units, or there are standard units that we can use, the so-called Hounsfield units. And here we see the range of Hounsfield units in this diagram, and that they relate to actual physical entities in your body. So for instance, very low Hounsfield units are mapped also to a very to structures with with low density. For instance, air has a very low density and therefore very low Hounsfield units. But the same thing is true for organs like the lung, because there a lot of air is in the lungs, and therefore they are also quite low Hounsfield units. In the middle area, we have structures with medium density, like water or also fat that is in the body, or sponges, bones. They are still low density, and then solid bones, of course, absorb a lot of X radiation and therefore have a high Hounsfield units. And when we look back at the image, we can already see how, at least in standard CT imaging, those intensities are mapped to actual gray values. So low Hounsfield units are mapped to color black or the very dark colors, while the mid-range area is mapped to gray values. Here we see the eyeballs that contain a lot of water, for instance. And then in the higher area, we use bright colors and end up with white here in the skull region. So now we have a basic understanding of the scalar values that make up our image, and we know that we have a lot of images. And we know also our visualization goal, because we want to create a three-dimensional representation of this specific body region. And in order to do this, we could stack those slides. And if we do it, a result might look like this. In this specific state where we just took the raw data and stacked them upon one another, we can't learn much from the data set because we don't see much. We mostly see a black block. Okay, we learn one thing from this black block, and this is that at least at the time point this scan was taken, the patient was in a good surrounding, because this patient was surrounded by air, and normally it's a good thing to be surrounded by air. So this is one thing we can learn from this very raw and direct visualization. But of course, we want to learn more. So now we have to apply our visualization pipeline. So we have to take this raw data that we see in the background there and have to do some kind of processing in order to add meaning to our visualization. And there are a lot of ways how we could process this rendering in the background there. But one very direct and suitable way for this kind of visualization would be to adapt the voxel representation itself. So voxels are the small building blocks that now make up our volume. And as we have more or less direct visualization, each of these voxels has a color that or a gray value that directly relates to the underlying Hounsfield units. But of course, we could easily change this visualization, for instance, by changing the opacity of some of those voxels. So we could, for instance, decide if something has a very low Hounsfield unit, then it has not that much density, and therefore we decide to make it transparent. And this, of course, is the standard way to deal with our visualization problem. We would, of course, render air that surrounds the specimen in the data set. We would render this air transparent instead of opaque black. But you could do a lot of different things. For instance, you could change the color of your voxel. You could, for instance, decide to make the brain red and the skull blue. But when you choose colors, you always have to keep in mind that these colors have a specific meaning. So I have a very recent but also very sad example where I can show you what I mean with this. So what we see here is a satellite image of the wildfires that are currently burning in the United States. And when you look at this image specifically, this shows you the areas that were in the specific region that were affected by the fire. And if you would look at it with a first glance, you would, at least I did it, you would assume that the red areas are the areas that are affected. But in this specific case, it's the other way around. Because if you look at the real color image, then we see that in the red areas, there are still some plants there. So I'm not sure why this color scheme was chosen. I would assume that the experts that deal with this data on a daily basis are familiar with this kind of color scheme, and therefore would misinterpret the red color for the affected area. But still, for us, as we are not that familiar with this kind of satellite visualization, we could jump to wrong conclusions. So you have always to be very careful when you apply colors. And you have, of course, you can choose from a broad range of colors, but your choice should also not only depend on what color basically mean, but also what your data represents. So in our case, we know that our data set consists of ordered, of linear data. As we know, the intensity of the voxels in our volumetric data set map to Hounsfield units and therefore to density. So this is ordered data. We could decide, okay, I want to also use an ordered lookup table. I map low density to bright values here and high density to dark values, and then choose a specific color layout. And this is suitable for our kind of data. But of course, it's not suitable for every kind of data, because if your data doesn't have any order, if you have just items that you want to separate by using color, then you should avoid using a linear sequential color scale like those examples. You would rather choose a qualitative color scale where all the colors have the same luminance and a strong visual distance, and therefore this would be quite suitable to separate different units. Here in the center, we see another kind of color scale, the divergent color scale that you might use if you have two sets of ordered data that belong to different classes and you want to visually separate those. So we have the two things. We have a separation by color, but still an encoding of order by means of intensity. Yeah, there's one color scale that is quite commonly used even today in the scientific field, and yeah, it's a quite old color scale. It's a so-called rainbow color scale, and it came up more or less the same time the first color screen devices were available. So I would assume this color scale was mainly used because it used all the color that were available. But in order to visualize, for instance, ordered data, this color scale is not optimal, because here this specific example has two problems, at least two problems. So the first problem is that we use a red color for the low and the high areas. So you could imagine if you have two data points in your visualization close together and they are both red, you won't know whether or not there's a very high and a very low value close together based on this coloring. But okay, you could decide to cut this red part and only map until purple, but still we see that there's something wrong with the perceived order in this data set. And this is because of the unstable luminance of this color scale. So we have dark areas, then bright areas, and dark areas again. So it's quite hard to map this color scale to an order. You wouldn't know that bright green might be lower than dark blue if you see those two data points side by side. And this is because our eyes are susceptible in a different way to different spectrums of the visible light. And as we use more or less all the colors that are available, at least on the screen, we see exactly this effect, that some colors tend to be brighter to us. And there's a third very basic problem with this color scale, and it's that a specific part of our population, for them, this color scale wouldn't be useful at all. And this is people who are colorblind, because we have big parts green and red in this color scale. You see that those areas would perceive more or less as the same, so the whole thing falls apart and is not usable to map a specific range. So therefore, when we choose colors, we have to keep in mind that the colors need to reflect the order or non-existing order of the underlying data. And we also have to keep in mind that the colors work for our recipients. For instance, when we want to make our color scales usable for colorblind people, there are only small adjustments needed. Here's an example for a divergent color scale from brown to green. And if we change the brown and green tones a little bit, then they are also usable for colorblind people. So now that we know that we can apply some kind of color to our visualization problem, I would suggest we do right that. We will now fix our visualization. And for this, I want to give a little live demonstration. So here you see a software system that we work quite often with at Fraunhofer Mewis. It's a very nice piece of software. It's called Mewis Lab, and it allows you to do various things. And one of those things is that you can create those networks, as we can see it, one example here. Those networks are made up of little building blocks, and those building blocks allow you to do some processing, apply some algorithms, and data flows through a network like this, gets processed, and then in the end we get processed data or also a visualization. In our case, we will get a visualization. So I loaded a CT data set, and here we see the slide, and we can slide through the data set. We see again that we are looking at the upper body part. Here we see the lungs filled with air, so very dark, and then we go through the head and we end up in the brain. And we also already from this 2D visualization of medical data can learn something about the data set, because as I mentioned, water, vessels, and the fatty tissue in the brain all have more or less the same Hounsfield unit. So we would expect a more homogeneous gray image of the brain area, but instead we see structures, and we see those structures because a contrast agent was given to the patient before taking the scan in order to make the vessels in the brain of this patient visible. So already we got some insight at least into the preparation process of the scan. And now if we stack all those slides that we see here upon one another, we get a result like this. So this black block of three-dimensional medical image data of some kind of anatomical data set, and we have to do something about it. And what we can do about it is, of course, change the color mapping. And for this, we can edit the so-called lookup table that is used to map Hounsfield units to a specific color. So here we have the color table that we're using right now. It's a very basic color table. It maps low Hounsfield units to black and high Hounsfield units to white, and is linearly interpolated in between. And we see that the opacity is 100% for the black values. So now we could reduce this opacity. And once we've done this to a certain amount, we can now see into our data set, because now all the air is transparent. And if we would do the same thing for also the bright values, then we would see how our data set visually dissolves. And then, of course, again, we see nothing anymore, because now every voxel in our data set is rendered transparent. Now I want to focus on this this graph that we see here. This is a so-called histogram, and it gives you information about how much voxels in your data set have a specific Hounsfield value. So we see, you might see it, this little peak in the beginning here. There are a lot of voxels that have a very low Hounsfield unit, so those voxels might be related to the air that surrounded the patient during the scan. Then we see another interesting peaks. Maybe we are interested in this little peak here. So what we could do is use our color table to focus only on a subset of our data set that relates to this peak. So in order to do it, we could add an additional point into our color table, make this point bright white, and then be surrounded by black and transparent voxels. So still we don't see anything, but now we have a new color scale that goes from black to white and to black again. And if we increase now the opacity of the voxels around this area and map them to the color white, do it right now live, then we can see that this peak and this area somehow relates to the bone structures in our data set. So we have done our first filtering based on the color table. I prepared an improved version of this color table, so for that maps to bones. And we can now use this visualization already to gain some insight about our data set, about our patient. For instance, we can have a look at the bones and see that none of the bones are broken. So this looks okay. We also see two bright structures in the mouth area of this patient. And now we learned that this patient had a tooth implant, and those implants are made of metal. And those metals have a high absorption rate when it comes to X-rays, so they are quite bright in our data set. But we knew earlier when we looked at the 2D slides that there's also some contrast agent was given to show the vessels. So we could also try to make those vessels visible by, again, adapting the color table. Now we have a color table that also has some red in the mid-range area. And when we now look into the skull, we can now already see this fine vessel structures emerging, but we still also see the bright bones. And if we zoom out, then we see these two interesting structures floating beside the head. So if we want to find out what this is, we could do a bit of exploration, and then at some point in time, we would find out that they have quite belong to structures with a low Hounsfield unit. So we add some bluish color in the lower area. And once we've done this, we could end up with the visualization like this. And we now see that those structures belong to some head fixture device that was provided to the patient so that he can hold the head still. We also see a cushion behind here. So now, we have learned some things about our patient, and we also have created a visually quite pleasing visualization of this 3D data set. And we only did it by changing color and transparency of the voxel to color mapping, intensity to color mapping. So we started with something like this, and in the end, we got something like this only by changing the color. So I would say this is a success, at least for this short example. And we'll now go back to the slide. And as we saw in the example, we now were able to, for instance, visualize the bones in our data set. And this is, of course, as we know now, that CT is quite sensitive to dense structures because it is based on X-rays. But our body is not made up completely of dense structures. There are a lot of quite structures with medium density, the organs, and they are also quite important when you want to get some insight about the physiological state of a patient. So we might need a different way of getting information from the patient. So instead of using X-rays, we need to use a process that is more reacting to components our organs are made of. And there's one process, so-called magnetic resonance imaging, MRI, that is exactly suited for this. And how does an MRI work? So an MRI scanner looks like this. It looks a bit similar to a CT scanner, but if we open this MRI imaging device, then we see that very big magnetic coils are inside the scanner. And these coils are used to create quite strong magnetic fields. So in clinical routine, those fields would have field strengths of about 0.5 to 1.5 Tesla, but this can go up to 7 Tesla even in very modern devices. And what this means, this Tesla strength, you can see here in this short clip, because this is a wrench and it's only held in place by an industrial fixture, because if this wouldn't be held in place, it would fly right into the scanner and do a lot of destruction. And this is why you are not allowed to take any metal with you when you enter an MRI scanning room, because this metal would fly out of your hand and into the scanner. And this is also why it's important for a patient not to have any implants in the body that react to magnetic fields, because those implants could heat up, and the patient could be hurt by this. So this is the magnetic strength that we are dealing with, and those magnetic fields, if they if they are at the patient, then we see what happens in the patient. The hydrogen protons in the body start to align with respect to the magnetic field. And the example is shown here. And what is done then afterwards is that a radio frequency, a pulse, is sent into the magnetic field. And when this happens, then those aligned hydrogen protons get spin out of their equilibrium due to the added energy, and they're straining against the pull of the magnetic field. And once this radio frequency pulse is turned off again, then those protons realign to along the magnetic field. And while they're doing this, they're also sending a radio signal. And around the patient, there are a lot of receiver coils that are sensitive to this kind of radio signal, and they can detect it. And yeah, then we can get parameters from this. So one parameter would be, for instance, the time it takes for a proton to go back into the to align back to the magnetic field. Another parameter would be the strength of the radio signal that is sent during this process. And yeah, from these parameters depend on the environment and also the type of molecule that is affected by it. So we can quite nicely differentiate between different types of tissue in the human body. And if we now map those parameters in some form to intensity again, then we would get images like this. And if you just look at them with a brief glance, then you would say, okay, this looks more or less like a CT image. But if we look closely, then yeah, I can do it. Then we see actually a lot more details with respect to organic structure. So now we see the muscles, we see details in the brain, we see other organs here. What we do not see are the bones. They are not that pronounced as they were in CT images. And this is because bones don't contain a lot of water, but they contain, they are more dense structures with less water contained. So now it's quite good if something contains a lot of water, because then we get a high signal from the scanning procedure. You could derive a lot of different parameters by the way you configure your magnetic field setup, also configure the pulses that you send into the magnetic field in order to get some kind of effect. And depending on this configuration that, as you can see here, can become quite complex, you can get interesting information about the water distribution in the body. Here we see an example, a resulting data set that resulted from a so-called PC MRI scan. And a PC MRI scan results in, for instance, 3 different blocks of those very noisy looking gray images. But the intensity in those images are quite interesting because they relate to the velocity of fluids moving in the body in a specific direction, X, Y, and Z. So if you combine those 3 blocks into one block, you have interesting information at each point, because now you know in which direction something was flowing at a specific point in time. So we get a 4D resolved data set that shows us how fluids are moving in the body. And again, when we look at this data block right here, it doesn't give us a lot of insight into the, for instance, blood flow of this specific patient. So again, we have to apply our visualization pipeline. And again, we want to do this with a small live demonstration. Now I will change to a different network. This is quite interesting because this network was really part of the bigger network that was used to create the movie that we will see soon. So I added some networks here at the site in order to give some insight into certain steps of the process. So that's why they look a bit messy. So we can look at the input data. Our input data is 2D 4D flow data measured with PC-MRI sequence and MRI scanner. And if we increase the brightness a bit, then we see this data looks like this. Yeah, so different intensities, but also a lot of noise. If we look at this in 3 dimensions, to wait for the final result. So if we look at it in 3 dimensions, it looks like this. So it's a block of gray value data. Right now, we encode only one of the directions in intensity. If we slice through the data set, then we can see we have this block of information here. We see already some interesting structures. And if we move through time, we can even see some movement that, of course, relates to for instance, heart movement, and we also see change of intensity. So something is flowing there quite fast. We again could guess that it's somehow related to the heart of this patient. So now, we want to create an actual visualization, and often the first thing that you do is to differentiate between useful and less useful data. In this case, we want to get rid of everything that does not relate to a vessel. And the result might look like this. So now we have a mask image. A quite sophisticated process was taken to derive where vessels are and what are not vessels in our data set. And then we might get a result like this. So now we have blood flow information only in the area of the vessels. If you look at this in 3 dimensions, we can already see, again, here density is mapped to velocity in one direction. We already can see some organic structure. So if I move this down here and we go a bit through time, then we see that the intensities are changing, and we also see a structure like this. This is the aortic arch, and we see some small vessels that lead up to the head, and downwards it leads to the lower body part. So we are in the right region. We see already the areas that we are interested in. So now we want to look at the flow, and for the sake of simplicity, we are now looking just at one slide, like this one. I will go to a different point in time, and here we see some structures on our slide. Of course, these are vessels. We see some intensities, those relate to the blood flow. And then now we could try the same thing that we tried earlier on. We could try to map some color table to our data set. And when we do this, we might get a result like this. Okay, now we see that, in the outer part of the vessel, there are some low values, and in the inner part, there are some orange values. So there's something high, the velocity is high. If we go through time automatically, then we can also see how this changes. So we have learned a bit, but not much. And what's the problem right here that we have? We tried again to use colors in order to visualize the flow, but this seems to be not a suitable way to visualize this. Instead, we should use some kind of different representation. So now we will have a look at the data points of our data set. And if I look at those data points, we can focus on this smaller vessel, for instance, or you can quite nicely see them. Then we see they are, of course, arranged in a regular way along the voxels of our data set. But using points is not very meaningful because our data set is not scalar, but this is vector data. So as you remember, for each point, we know the direction of flow. So when we use vectors to visualize this part of the data set, then we start to see some interesting structures. So in this case, we see some swirls, we see change in direction. We can also see that something is moving out of the plane. If we look below the plane, then we also see something moving in this direction. So now we have a first idea of the direction of blood flow in this specific slide. So if we again change our points in time, then we see how those vectors are actually moving and changing over time. But still, we are omitting a lot of interesting, useful data around this slide. Now, for every slide above and below the slide, we have similar information, directional information. And we could use a different visualization technique, for instance, particles that we start and let them move along this changing vector field. And once we do this, we can get an image like this. So now we have a specific point in time, and we let some particles move along the vectors. And now we see, for instance, that those two parts were actually connected. They belong to the same vessel, to the aortic arch. And if we look below our slide, we can see much more qualitative information about the blood flow. We see the swirls, and if we even change the blood flow over time, we can now gain a very nice look at the dynamics of the blood flow and how it changes. You see the ejection phase into the aorta and down to the lower body parts. So this visualization that we saw right there was created with a different goal in mind. Our goal was to actually get a quite nice look at the blood flow, but in real applications, blood flow visualization might look different. One example is here, deals with the coarctation of the aorta. That's a disease that often occurs in children. And then some part of the aortic arch is too thin, and this leads to a lot of stress for the heart. And there's one project of ours that is quite interesting in this scope. And this project uses, again, flow visualization to visualize the difference in pressure that was also measured. And this is quite nice because we get a lot of information about the pressure difference. We get a three-dimensional look on how the pressure is distributed in the vessel. And also, the child didn't need to get a catheter inserted. So we were able to just use imaging in order to get this kind of insight. So this is what flow visualization would look like in a more clinical context. And yeah, as you see, visualization is always part of a bigger pipeline, always part of a bigger system. It's not standing alone, but at a certain point, it makes sense to look at the data to get an insight. Other examples would be the visualization of fibers in the brain, which you want to visualize in order to plan an operation so that when you enter the brain, for instance, to remove a tumor, you don't hurt that much of those fibers, and a lot of the cognitive capabilities remain afterwards. Another example would be treatment planning of the liver. When you have to remove, for instance, part of the liver, you want to keep as much of the remaining liver alive, and therefore you have to plan very carefully where you cut in order not to hurt that much vessels. And the planning could look like this. Here in yellow, we see the planned cut. And you could even take this information with you in the intervention itself. Here we see an example of how those visualizations are used to improve the treatment by overlaying the actual organ with the planning information. And there are a lot of other examples, but I would say I don't have that much time left in order to focus on those examples. So if you are interested in what we are doing, you could visit, for instance, our homepage where you see the different projects we are working on. And you could also visit our YouTube channel. And as I promised in the beginning, we now want to look at one of the movies on this channel that we created, because now you have background knowledge and a better idea on how those images were actually created. So I will just show you the movie. Here we see again the stacked slides and stacked to create a volumetric image. And now we applied color to this data set. And in this specific case, we used a diverging color scale. So we have blue and green areas for the rib area and the upper parts of the lung. And we have chosen orange for the heart in order to visually differentiate between those structures. What we can also see is this is a 4D data set. So the heart is actually changing. We get the shape of the heart at different points in time. And as this is a tomographic image, we can also slice through the image because there are a lot of information inside. And if we do so, we reveal some internal structures, like, for instance, the muscle that you can see here. Also, the valves in the heart that are opening and closing during the cycle, here superimposed with this overlay. Yeah, and we know that this kind of image is based on CT. So when we look at the intensity profiles, we get a high signal for structures with a high density. So we see that the bone has a high density. There's an object with an even higher density. This could be related to a stent that was implanted into the patient. And if we switch the modality, we can show even more related to the heart. We can now show moving fluids. And yeah, if we adapt our visualization techniques to use, for instance, vectors like this, or even particles, then yeah, we get a quite nice look at the blood flow itself. Oops, no, I stopped the visualization. Nope, we lost it. Yeah. So with this movie, this brings me to the end of my talk. So we learned a lot about the visualization pipeline. We had some examples how we come from raw data to meaningful images. In the scientific scope, meaningful means that we want to be as informative as we can get from the data set. But of course, as we see in this example, if you just have a different visualization goal, like to be a bit more inspiring, to create visually pleasing images, then you alter the visualization pipeline in order to reach this goal. And we also have to keep in mind that we can't visualize everything that is present in the body. The scanners have boundaries in terms of resolution and accuracy, and also we filter a lot while we visualize. So I would say there's still a lot of open space that is available for yeah, a different interpretation beyond this strict data-driven path that I presented today. So thank you for your attention.
Thank you so much. That was super fascinating to see it deconstructed in all levels, and then to finally see the animation that people just think just happens and they don't realize how much time and work and data and visualization and issues around color, all those different things going on. Really, really fascinating. I certainly would love to be your student and learn more. So I'm very happy that one of our ArtSci member, collective member, Eli Joteva, got a residency, because through her work and my being on the sideline as an advisor, I will actually learn more. So Ellie's going to go on next, and she'll talk from her perspective as an artist. But I'm really, really grateful, Dr. Neugebauer. I'm sorry. Neugebauer.
No problem.
Sorry. Thank you so much. Much appreciated for your talk. And it will be a piece that we can go back to and show to our students as a way to introduce to medical imaging and how important it is right now with all the health issues that the world is facing. It's a whole new planet. So it's really, really important work. And artists are honored to have part of that. So thank you again. Dankeschön.
Okay.
All
See
right,
you.
so bye bye. So we will move